Hello, my name is Connor Tucker for Team 50 of the Senior Design Spring 2020 semester. Clean water is essential for human life and health, though an estimated 11% of the world's population does not have regular access to clean water. Desalination of seawater is becoming a common way to provide that water to areas where it is scarce. Reverse osmosis was found to be the best solution for desalination, but it is energy intensive. Our team decided we wanted to try and power a reverse osmosis system with solar energy because it would be more sustainable and deployable. Our mentor, Dr. Hansberg, had a research project that fit our scope, so she brought us onto that project. I'm going to hand it off to Jason Wenke to talk more about it.
So we joined the project partway through, and as you can see, the unit was broken by the time that we got to begin working on it. Several key components, such as the end caps, were busted from over 2 years of non-maintenance. Project scope is to produce 300 liters of farmable water per day and run off completely powered by solar panels. The project is going to be sent down to Point Lobos, Mexico, where they do not have access to either clean water or grid power, so that's why we have these parameters. The entire project is also in collaboration with the University in Mexico. I'm now going to hand it off to James Soriano.
So in order to power that desalination unit, we are going to use solar panels. And in order to simulate the electrical performance of the panels, we use Python. The parameters of the solar cells are based off of those manufactured at ASU's MTW facility. These solar panels will be mounted at a 30-degree tilt, and we utilize TMY data, which is the typical meteorological year data from Chula Vista Brownfield, which is the closest city with available TMY data to the final home of the system. And after multiple simulations, we narrowed down two ideal configurations. One is a 30 module configuration without a battery, and another one is a 15 module configuration with a battery. And now I'm going to hand it off to Emilio Trujillo with the results from that simulation.
From the Python code, we got the outputs of the short circuit current of every hour of the year based on the sun's position and intensity, and that is shown in this first graph here. We also took the temperature from the Chula Vista TMY data because the temperature has an effect on the efficiency of the solar cells. Using that temperature, we calculated the module's temperature at every hour of the year because of the effect on efficiency. And then we were from that able to calculate the amount of energy produced at every hour of the year with temperature dependence per square centimeter, so we could fit how many modules we would need to power the load of our system in the desalination unit to have it running for the desired amount of time to produce 300 liters of water. The two configurations we used were with a battery and without a battery. We used a battery and obtained availability of about 97%, which is great. You can run almost 100% of the time. Compared to that of without the battery, it's only around 90%, so you have some downtime. Not only do you have some availability suffrage there, but you have to have double the amount of area for twice as many solar panels, which can be an issue. So the way to go is with a battery, and you'll have almost 100% availability.